So what I want to do now in this video is apply what we talked about with the flux, finding flux through a Gaussian surface to 3 different problems. Just to get some practice here, and I put some actual numbers here so we could do some calculations. And just to remind you that we're looking, when it comes to picking a Gaussian surface, when you're trying to find flux in our problems, we want to make sure this criteria is met here, okay? So that electric field must be constant anywhere on the Gaussian surface. So you pick the Gaussian surface, we just have to ensure that the electric field is constant anywhere on it. And also the electric field must be perpendicular to the surface anywhere on that Gaussian surface. Okay, so we pretty much do this by picking the right symmetry. All right, we got to choose the right symmetry for the problem. If we do that, that simplifies, this integral here for flux to just EA. Okay. So that's our goal, and so let's do our first example. So our first example is just a point charge. So a -3.2 nanocoulomb point charge is located at the origin. What would be an appropriate Gaussian surface for this problem? Okay, and then so we're going to decide that, and then find the flux through a surface that is 15 centimeters from the point charge. Okay, so let me draw the point charge first. The point charge looks something like this, and I'll draw or put it's a negative, so I'm gonna put a negative here. That's -3.2. All right, and we know we have electric field going radially outwards in a spherical fashion, right? For point charges, that's the kind of electric field, that's the kind of symmetry we have with the electric field. So if we're dealing with a spherical symmetry, right, for electric field, it'd probably be best to choose a sphere. So I'm gonna choose a sphere. Oops. Okay, so there's my sphere. I try to put my charge right in the center of the sphere as best I can. All right, and so I know that my electric field here is constant throughout, right? Electric field is always, actually wrong direction, because there's a negative charge, right? So I gotta go a little slower here. On the surface, I have electric field going like this, okay? Going towards it here. Trying to keep this about the same length, but I'm not going to get perfect. Okay, so here's my electric field going towards the negative charge, right? Which is, we talked about that in chapter 22 or 23. That electric fields from negative charges always point towards the negative, always point towards the charge. Okay, so I have electric field. We know it's uniform or constant along this sphere, along my surface. What about my normal direction? Remember what I said in the last video, the normal direction, we define it to be pointing outward from my surface. So it looks something like this. I'm just going to draw one. Okay, so that's my normal direction. Okay, so let's ask ourselves if those conditions are met. Do we have to use this equation here? E dot dA, or can we simplify that? Well, along the surface, electric field is constant. Okay, so that's good. It's supposed to be a vector here. Okay, so electric field is constant, and also along the surface. Now, electric field is not parallel to my normal, right? I can't say electric field is perpendicular to my surface, so I can't simplify this to EA. But there's something unique here that we didn't see in previous pictures, is that N and E are opposite, are going in opposite directions. They are what we call anti-parallel, right? Going in opposite directions here. So how does that affect my flux? Well, remember we said that that's going to give you a negative flux. If your electric field is going the opposite direction as the normal, you can get a negative flux there. Okay, so that's our equation. Now it's just a matter of finding E and A. Okay, so we're looking at the electric field at what distance? What's this distance here? Well, for part B, we're finding the flux through a surface that is 15 centimeters from the point charge. So let me put a little radius here. So that's a 15 centimeters. So I could calculate my electric field. And my electric field, E, is just using KQ over R squared. Okay, or I could rewrite this. Okay, so I'll get the electric field there in a second. So that's E. What about A? What's my area for this? Well, let me, one more thing here before, just to be clear, this R squared is a distance from here to there, right? So that's 15 centimeters. From here to there, from here to there, right? Anywhere on this sphere, it's going to be the 15 centimeters. All right. What about area? What area are we using? Well, we're looking at the area of a sphere. So area of a sphere is 4 pi r squared. Okay. So let's plug this in. I get negative. Let's see, E. Oops. Q over R squared. Now this Q, because I already took into account the fact it's negative here. So I'm just going to look at the absolute value of Q. Okay, that's how I determined that it's going to give me a negative flux. All right, because again, the electric field is pointing in for negative charges. Times the area, 4 pi r squared. And look at this. The 4 pi's cancel. Let me write this a little bit neater over here. Okay, 4 pi. So the 4 pi's cancel here. And also the r squareds cancel. So what does that leave me for my flux? So my flux, oops. Let me get black again. Equals negative absolute value of Q over epsilon 0. Really interesting. So a couple of things, well, and of course we could plug in our numbers, right? So we get a negative 3.2 nanocoulombs over 8.85 times 10 to the negative 12. Okay, and let's plug that into a calculator. I still need to replace the batteries on my calculator. What do we get there? Okay, so 3.2 times 10 to the negative 9 divided by 8.85 times 10 to the negative 12. All right, so I get about, let's see, 3.2. So I get negative 360. Okay, so negative 360 there. And the units for that is newtons meter squared per coulombs. That's the unit for flux there. All right, so a couple observations here for flux. It's kind of interesting. It doesn't really matter on the radius, right? It didn't matter that I said here 15. Nowhere did 15 come in my final calculations, right? The radius canceled out. So what does that tell you about flux? That tells you that it doesn't really matter how far you are from the charge. If you look at a charge that's really close, let me say this again. If you look at a Gaussian surface that's really close, okay, so a lot smaller. Why does that give me the same flux here? Why do I get the same flux here as I do over here? The reason for that is because even though you have a smaller area, right? You have a smaller area here. Even though you have a smaller area on the sphere, you have a larger electric field, a stronger electric field. So these electric fields here are, okay, that's way too big. Let me get a little smaller here. I'm trying to draw it, but okay. So that these electric fields, because they're closer to the charge, right? This point, the sphere, my Gaussian surface here, my imaginary surface, we're looking at electric fields that are located closer to the charge. So that's going to give us a stronger electric field, even though we have a smaller area. Okay, so that ratio, E and A, kind of working with each other so that you always get the same flux, whether you're looking at a smaller area or whether you're looking at a larger area. You always get the same flux. So what does flux depend on if it doesn't depend on area or distance? It just depends on charge. And this is what is at the heart of Gauss's law. Gauss's law says that all you need to know in order to calculate flux is just how much charge is inside that Gaussian surface. Another kicker is that I'm making a big deal about choosing the right symmetry, right? Choosing the right Gaussian surface so that you could avoid this integral. It turns out for Gauss's law, if we're not applying Gauss's law quite yet. This is not Gauss's law. This is just flux. But Gauss's law says that it doesn't really matter what shape you pick in order to find the flux. As long as you know the charge inside, you're good. Okay. Now, if you're going to calculate flux without knowing the charge inside, if you didn't know how much charge was inside there, yeah, you definitely want the symmetry to make this easy. But if you know how much charge is inside, right, Q, then it's just as simple as doing charge over epsilon 0. And that's what we did, right? In order to get our flux, all we did was charge over epsilon 0. And we got our answer. Okay. So, and this kind of goes back to what I started with the last video on, that you get, if you have a negative charge in there, right, the arrows are pointing inwards, then you're going to get a negative flux. Okay, so kind of neat little characteristic that flux doesn't really depend on the radius, assuming you're matching the symmetry here. Well, I guess even if you're not matching the symmetry, you're still going to get the flux, the same flux. It only depends on charge inside. Okay, so let's try another one. Here's another example. So we have a line of charge this time. So not a point charge, a line of charge. What would be the appropriate Gaussian surface for this? So let me just sketch out my line charge here. So let's say here's my line of charge, and it is an infinite line of charge. And we know the electric field is going, we're going to take this to be a positive number. So we know the electric field here will be looking like this, right? Going out kind of perpendicular to that wire. Okay. All right, so so the first question here, what would be an appropriate Gaussian surface for this problem? So what kind of symmetry do we have here? Well, we have cylindrical symmetry, right? Remember, I had this at the end of the last video, that if you looked at this, at the cross-sectional area, so you, instead of looking at it from the side, instead of looking at this infinite line of charge from the side, let's say you looked at it head on, you would see something like this. So the wire, let's just assume it's a wire, has like that, right? And the electric field will be going radially outwards. Something like that. Okay, so that has the, you know, the cylindrical symmetry. So because of the cylindrical symmetry, the best Gaussian surface we could pick would be a cylinder. So I'm gonna pick my Gaussian surface here. Again, my Gaussian surface is an imaginary surface. It's not interacting with this. It's just, all it's doing is simply enclosing this charge. So I'm gonna actually, let me move this a little bit. Now, my Gaussian surface, oh, come on, there you go. My Gaussian surface is not going to be infinite. Okay, it's going to be a fixed distance. So let me draw it, finish drawing it here. I'm trying to make this straight. Okay, and then I have another sphere here. Oops. Okay, so something like that. And I can connect this line here to make it my cylinder. Okay, and then I could draw my cylinder over here as well. Okay, so let's calculate the flux here. All right, let's calculate this flux. So find the flux, this is part B now, find the flux through a surface, which is, we chose a cylinder that matches the symmetry, a surface that is 15 centimeters from the line of charge. So I'm going to draw my radius here. I could make this a little bit thicker so we can see it. Okay, so that radius, 15 centimeters here. Okay, so let's calculate flux. Well, we essentially have, we're going to calculate flux here. We essentially have these three different sides. You have the front end, you have the back end of this, if you kind of picture this as a can, right? The right side of the can, the left side of the can, and then you have the sides here. You have the sides. Okay, so we want to calculate the flux going through each of those. So my total flux for this wire would be equal to the flux going through the right end, I'm going to put R here for the right end, plus the flux going through the left end, plus the flux going through the sides. Okay, so let's talk about the left end and the right end. Do I have any electric field going through this surface or going through this surface? In other words, do I have electric fields kind of penetrating that surface like that, right? Or like this, or having any kind of component that is perpendicular to this circle? And the answer is no. All your electric fields are going to be going straight up, straight like this. So you actually don't have any electric fields going through the surface, which is telling us that the flux going through the left end and the right end of the cylinder is going to be zero. Okay, so, whoops. So we get zero flux there plus zero flux there. Now, what about the flux on the sides? How do we calculate that? So the flux on the sides here, we have, and it's kind of hard to see here. All you see here are the vectors going down and up, but really you have vectors coming out towards you as well, right? And this is why I drew this picture here. You have electric fields going kind of radially outwards in all directions. So it's a little harder to see that on the side view, but if you look at it head on, you can kind of see that electric fields there. Okay, so we are equidistant from that wire, right? All these electric fields are equidistant from this wire, and so that's good, right? So also, I forgot my point here. Electric field is equidistant from the wire, so that means we have constant electric fields there, and because we're matching the symmetry, all these electric fields are perpendicular, right, to your surface. So we could calculate electric field just by EA. Okay, so what E are we talking about here? Well, the electric field for a line of charge is 1 over 2 pi epsilon 0 lambda over R. Right, where R, in this case, we're trying to find the electric field on the surface here. So it would be this 15 centimeters. Right, if you want to see in this picture, that 15 centimeters is right here. 15 centimeters there. Okay, so that's the electric field. What about the area? The area of a cylinder sometimes is a little hard to see. We need the area of this area here, right? All this, the sides of the can. Okay, so the sides, if we want to find the sides, it's best to think of it as a rectangle. Okay, like almost like if you imagine like a piece of a roll of toilet paper, and you roll it out one whole revolution, right? You're left with this much toilet paper on the floor. Okay, so or paper towels or whatever it is you want to think about. Okay, so if I unroll this can and just stretch it out, get the sides and stretch it out, what are the dimensions of this can? So what we're going to have here is that one side, the longer side here, is going to be my 2 pi r. Right, That's one. That's the length of one. That's the circumference, right? If I take that circle or that cylinder and roll it out, you know, this way. So that, you know, I start the can here and I roll it out this way. Well, that distance here is 2 pi r. What's this distance here? Well, this distance would be whatever the sides of the can are. So I'm just gonna call this L. Okay, so L. So the area of the sides is just 2 pi RL. All right, I'm gonna have to move this because I'm running out of space really quick. Okay, so my flux, what's my flux then? Well, let's put those two things together. Electric field from my wire, 1 over 2 pi epsilon 0 lambda r times EA, or sorry, that's E. I just plugged in my E times A. A is a let's see, 2 pi RL. Okay, so a couple of things cancel here. We get 2 pi's cancel out, right? And then r's cancel, and we're left with flux equals lambda L over epsilon 0. Now, one more substitution here. Remember what lambda is. The lambda inside this cylinder is just equal to the charge inside that cylinder over L. All right, so if I make a substitution here, solve for plug in for lambda here. Now make a substitute, take lambda, plug it in here. What happens? Well, we get exactly what we got last time, Q over epsilon 0, charge over this constant. And that's all you really need to know to find flux. So again, we get Gauss's law back. This is what Gauss's law said. Gauss's law says flux equals Q over epsilon 0. Okay, so finding flux is just a matter of knowing how much charge you have inside your Gaussian surface. And again, you can kind of see here, it doesn't really matter on what this radius was. Right? In my final answer, do I use the 15 centimeters? Well, I guess I would have to use this in order to find flux. I just realized that you need to know the length here in order to get an actual number. But my point in doing this example is to show you that flux just depends on Q, the charge inside here. Let me highlight that. All right, it's just this charge right here. Okay, I can highlight it with a little darker. Right, this charge. Okay, so it's just a charge inside my Gaussian surface divided by epsilon 0. That's all you need to know flux. You don't need to know the radius. You don't need to know the length, really. All you need to know is how much charge is inside your cylinder divided by epsilon 0. All right, now all that to say, doesn't mean we don't ever need to use this. We will use EA quite a bit. All right, so we do need to know this process here that I'm showing you. But we're getting back Gauss's law over and over again. All right, one more example. And okay, if you really want to get a number for this example before I move on, you just make L equal to 10 centimeters or something, right? And then you can calculate this, right? Lambda, you know, 2.5 microcoulombs. L, I now gave it to you, is 10 centimeters, and epsilon 0, it's a constant. Okay, so you can calculate flux, but again, that's not the main point of this example. All right, last example that we're going to look at here. So 3-point charges lie on the x-axis. Okay, so let me draw this out actually. Draw my x-axis here and the origin. Okay, so we're going to have one charge here, the origin. Another charge, let's see, at x equals plus d. Okay, and another charge of x equals plus d. X equals minus d there. Okay, so I know I don't say this in the problem, but let's just say they're all the same charge. So plus q, plus Q. All right. The question here is, what is the flux through a sphere centered at the origin with a radius of d over 2? So I'm going to make a sphere here, my Gaussian surface. Let me pick a different color. That's pretty close. Okay, so there's my Gaussian surface at d over 2. Right, so that's my radius here. And so I'll call this d over 2. Okay, and that the distance between each charge here, or each adjacent charge, is d. I'll put that different color. Okay, so let's see. We're trying to find flux. So the first question I want to answer here is, what about, how do we find the flux for charges on the outside of a sphere? Okay, so let me draw this one, the positive, the one on the right. Let me just redraw that down here on the bottom. And I'm going to draw my Gaussian surface again, but this time just the surface itself. Okay, so I have this positive charge off to the side here. Positive charge. And that part charge is giving off an electric field. Okay, so that electric field is going to be going through this surface, like this. Okay, and it continues through that surface. Like that. All right, so what's happening here with this flux? So you have a whole bunch of flux going into the surface. Now, that flux going into the surface, where's my, here we go, right here, electric field going into the surface, and that would actually be pretty hard to calculate, right? Because you see, not only is it non-constant, right? Because you're getting further and further away from the charge. So the electric field here is not constant, the angle is not staying the same. Okay, so this, you would have to use that integral E dot dA to solve for this, for the flux. But my point is here, just looking at this conceptually, you have electric field going in, that gives us a negative flux. Okay, and if flux depends on two things, right? Flux depends on area and E. So I'm gonna put EA here. Even though that's not how you would calculate flux, right? It's not just EA, but it depends on those things, electric field and area. So here we have a pretty strong electric field, right? Because we're closest to this point charge. Gives us a lot of electric field, although you can see the region here. Draw a little circle. Right, the region of the sphere that's going into is pretty small compared to the region of this sphere here, where it's coming out. Let me erase that. Okay, so it's kind of interesting. We have a lot of electric field, smaller area, that gives us an overall negative flux here because it's going in. Well, over here, now we get a positive flux, but this gets a larger area, right? Because that electric field is now being spread out as it goes through the sphere. It exits with a larger area, but the electric field is weaker. Okay, so we need to take into account all those things. If we take into account all those things, right? So a negative flux with a large area, sorry, let me say it again. Negative flux with a large electric field, small area. Positive flux with a large area, small electric field. What we see is that the negative electric field, or negative flux here, which is coming from the flux going in, is going to cancel with the flux, well, with the positive flux. And that's a flux going out. Okay. So electric field or charges on the outside do not give you a flux through a surface. You do have flux going in, flux going out, but the net flux, the overall flux through this Gaussian surface here is going to be 0. So this charge here and this charge here do not contribute at all to the flux through this. You get a 0 net flux from this charge, a 0 net flux from this charge. So there's no flux from these outside charges going through this Gaussian surface. The only one that gives us the only one that gives us a flux through this Gaussian surface is this positive charge here, which is what Gauss's law has been saying the whole time. Flux equals charge inside your Gaussian surface over epsilon 0. In this case, our flux is just going to be what's inside. Well, inside is just a Q, 1Q, epsilon 0. That's our flux. Okay, so we're starting to see that connection between flux and the charge inside. I think you could kind of see that working itself out, even when we're not deliberately trying to find charge. You know, in all our examples, we look at charge over epsilon 0, charge over epsilon 0 right here. So in every single one of our examples, we end with charge over epsilon 0. Okay, now like I said, we still need to know how to do this. I can't just skip the step every single time, because the main reason or the main use of Gauss's law for us is going to be to solve for E. We're going to solve for E in somewhat complicated situations where Gauss's law really gives us the tool to solve for E that we didn't have otherwise. Okay, so we're still going to do EA. We're still going to have to think about what area are we plugging in. Like in this case, we did 4 pi r squared for the sphere. In this case, for the cylinder, we did 2 pi RL. Okay, so we're still going to work that out. But flux will always equal the charge over epsilon 0. Okay, so our next part, in the next video, we're going to dive into how do we actually calculate Q inside. In this example that I show you is pretty easy, right? Well, Q inside is just Q. Even here, it was on the easier side. You just had to use this lambda equals Q over L. But there are going to be examples where finding Q inside is not a trivial matter. It's going to require some integrals. It's going to require some thought. So in our next video, we're going to talk about that. How do we find charge inside?